So we're going to do a quick review of heating and cooling curves. Right, so remember that temperature in degrees Celsius is on the Y, and basically the progress is on the bottom. Right, so for this one, because we're dealing with water, we're going to have 0 degrees Celsius, 100 degrees Celsius. It's going to be significant. We'll start out with down here at like -10, and we'll just take it up to 120. So we have our graph. Right, so this is really a heating curve of water, right? We're going to heat our water up. Now you can do this with any substance, right? You can do it with water, you can do it with alcohol, whatever. You just have to know the different values, right? But here, get out my plug in here. Okay, so there's 5 parts to this graph for this one. Right? Not every problem has 5 parts. You just gotta start and stop. Depends where you're starting and stopping, right? You're heating or you're cooling. Okay? But every diagonal, every plateau is a special, unique place that you need to do a special, particular type of calculation at. Okay, in this case, we're going to do 5 calculations as we warm water from -10 degrees Celsius all the way up to 120 degrees Celsius. Okay, so what is happening at the plateaus? What's going on at the plateaus? Yes? Yeah, change of state, right? Phase changes at the plateaus. Right, phase changes at the plateaus. That means delta T is 0, right? Which means we cannot use Q equals MC delta T. All right, so we have to have a different approach. All right, we need to use, because delta T equals 0, we have to use the delta H of fusion or the delta H of vaporization. So that's just the amount of heat needed to melt or freeze 1 mole of water. We know what that is. It's a given amount. Delta H of vaporization, the amount of energy it takes to heat or condense, right, to boil or condense 1 mole of water. Okay, and those are known values. So those are going to be given values to you. There's a list of given values that we need to be aware of that you'll always be given. Right, delta H of fusion is equal to 6.02 kilojoules per mole. Okay, delta H of vaporization is equal to 40.8 kilojoules per mole. Right? And then at the diagonals, on the diagonals, we're always going to be able to use Q equals MC delta T, because you got a temperature change happening at all the diagonals. Right, so we've got to give you some C values. So the C specific heat for ice is 2.11 joules per gram degrees Celsius. Specific heat for liquid water, right, is 4.184, like you know. And then we have to have a specific heat for steam, right, water vapor. And that is 2.01 joules per gram degree Celsius. All right, so you're always going to be given those values. All right, do you guys remember this? Okay, so we're going to rip through one problem that has all, where we have to do 5 questions. Well, we have to do all 5 calculations here. All right, so kind of the typical question that you'll see will be something along the lines of how much energy, right? And with energy, they're talking about heat here, is needed to heat 100 grams of water from negative 10 degrees Celsius to 120 degrees C. Okay, that's really what we're doing. Okay, so we have to, at every change on that we go through on the diagram, on the heating and cooling curve, we have to do a calculation. If we're on a diagonal, we have to do a separate calculation from the plateau, and so on and so forth. So in this case, we're going to do 5 because we're going from a solid, we're going to warm that up, then we're going to melt it, then we're going to warm that up, then we're going to melt, then we're going to boil it, and we're going to warm up that gas. So there's 5 different steps we're going to do here. Okay, we can't just go from 10 to 120, right? Because we have different substances along the way, right? We have solid, we have ice, we have liquid water, we have water vapor, right? All those have different specific heats. And as you melt or you boil them, it's different amount of energy to boil or to melt. Okay? So here we go. First step, Q equals MC delta T. Right, we've got 100 grams of water. Oh, we got ice, right? 100 grams of ice, 2.11 joules per gram dot degrees Celsius. And our delta T here is just going from, right, initially 0 up to 10 degrees Celsius. Or I'm sorry, from 10 degrees Celsius up to 0, so the delta T is 10 degrees. I think it's 2100. 2.11 times 100 times 10. Yep. Let's quit moving. So 2,110 joules. We got 2,110 joules there. So there we go. That's the first step. Now we've warmed all the water up to 0 degrees Celsius. So now we have to melt the water. Okay, now we have to melt the water. So we cannot use, we need to melt, delta T equals 0. So we cannot use MC delta T. So we have to use a different equation. We need to know the moles of H2O because we're going to multiply that by the delta heat of fusion. It's kilojoules per mole. We take something that is kilojoules per mole and multiply it by moles. Moles cancel and we're left with kilojoules. Okay. So moles of water here. We're going to figure that out. We got 100 grams of water and 1 mole of H2O. We've got 18.02 grams. And it's 5.55 moles of H2O. Okay, so I'm just going to plug that in. So we got 5.55 moles of water. We're going to multiply that by the delta H of fusion, one of our given values there. All right, 6.02 kilojoules per mole. That's 33.4 kilojoules. Remember doing all this stuff a while ago, like October. Okay, in the third calculation, so we're right here now. We're on the next diagonal, right? We have liquid water at this point. We've melted all the water, so we can use Q equals MC delta T again. We got 100 grams of water, 4.184 joules per gram degree Celsius. And the delta T here is 100 degrees C. All right, so this is 41,840, but yes. That's joules. That's in joules. Okay. Next step, number 4. We're going to boil. Right. So we got another phase change. So delta T is 0. We got to do the same equation as before. Moles of H2O times delta H of vaporization now. Right, a vaporization because we're boiling. We got heat that is specific to that phase change. So we've got 5.55 moles water. We're going to multiply that by 40.8 kilojoules per mole. So we got 226.4 kilojoules. All right, last step is number 5. And the Q equals MC delta T because we got a temperature change happening. So we've got 100 grams of water. Now we have steam that we're warming. So that specific heat is 2.01 joules per gram degree Celsius. And our delta T is 20 degrees C. 20 times 2.01 times 100. So I got 4,020 joules. Kind of shrinking this down so I can fit it all on one screen here. Okay, so those are all 5 steps there. All right, now we're not done yet because we want the total amount of heat, right? Total amount of energy. So to add them all together, we need the total. The key here is units, right? Units got to match. Kilojoules and joules do not match. Right? They're different by a factor of 1,000, right? Okay, so I'm just going to, since we have 3 of the 5 are in joules, I'm just going to go to joules. If you want to use kilojoules, more power to you, okay? It doesn't matter. You get the same answer, just in kilojoules, which is just fine, okay? So first step was 2,110 joules. Second step, it's kilojoules, so we got to convert that, so that's going to be 33,400 joules. Third step is 41,840 joules. Fourth step is 226,400 joules. And the fifth step was 4,020 joules. We just got to add them all together. So I got 307,770 joules, or 307.77 kilojoules. Okay. you go. Okay, so that's our review for heat and cooling curves. You can do this for any substance as long as you know the specific heat values for their solid, liquid, and gas phases and their specific delta H of fusions and delta H of vaporizations and stuff. So given the known values, you should be able to do it for any substance, okay, not just water. Any questions? Great. Okay, next thing, triple point diagram. Here we go. So triple point diagrams. These are AKA, these are also known as phase diagrams. And I also call them butt diagrams. Okay, B-U-T-T diagrams. And I'll show you why in just a moment. Okay, and really what these are doing, these phase or triple point diagrams, they are they allow you to see the state of matter for a substance at a particular pressure and temperature. Okay, they're a graph of pressure and temperature and phase and states of matter. And it's really just what they are, a graph of. All right, so here's a typical, this is for most substances. Typical substance has a phase diagram that looks like this. Pressure, temperature. All right. And it looks something along these lines. Something like that. We'll label in just a second. Let's draw that a little bit. Okay, so when it's really cold, what are most things? What? Solid. So like when temperature's really low down here, right? This is the solid area. As you warm things up, they become a liquid. Right, and then the reason why it's called a butt diagram, right? There's the crack. Out of the crack comes the gas. Okay. So you always know where the gas is. And then obviously you gotta go back the other direction. Right, it's all liquid gas. So there you go. That's why it's a butt diagram. Funny? No? Mildly amusing. All right. So there's two. I have 2 points kind of dotted on here. Okay. There's this point here. This is the triple point. Right there. And right there is the critical point. All right, the triple point and the critical point. The triple point is an interesting place where all 3 phases of matter exist in equilibrium with each other. There's liquid, there's gas, and solid all at one time. Okay, and they're all going back and forth in equilibrium with one another. Okay, that's why they call it the triple point. Okay, all states of matter are present at the same time. The critical point is the point at which gas will no longer condense. As pressure and temperature increase. Okay, so as you're increasing, as it would go longer there, right, the gas no longer would condense at that point. Okay, because there's so much pressure and the temperature is so high, gas would no longer condense. Okay. So those are kind of the 2 points to be aware of there. But really, what is this showing you? Okay, it's showing you how pressure and temperature affect phase. Okay, and how if you were to take a point, for example, maybe some different color. If we were here at some point, and while we have pressure constant, we lower the temperature down or increase temperature to that point. What is happening as you're going from here to there? Okay, specifically? Okay, what do we call that? Okay. There we go. We're melting. That's pretty much what we're looking to do here. Right? You have to just be able to read the graph. Here's this point. If we lower the pressure down to whatever, what happens? Right? Vice versa. So like this. Go from here. Oh, we're going to lower the pressure down to this point. There. What happens? Vaporization or evaporation, whatever. And there's probably one that we don't remember. What is it when you go from a solid to a gas? When you go from a solid directly to a gas? Or from a gas directly to a solid? Remember? Solid to a gas. With an S. That's stupid. Okay. Sublimation. Okay, sublimation. What about from a gas to a solid? This one is, I totally understand if you don't know this one. A weird one. If you're going to put money in the bank, you're making a what? Deposit. Yeah, we call it deposition. Okay, those are the two that I would expect you to probably don't know, but now you know. Okay, all the other ones, all the other phase changes you should know. Melting, freezing, evaporating, condensing. Okay, you should know those. Right. All right, so that's that. Now, we'll do one other phase diagram here I want to point out to you. So that's pretty much every phase diagram for a typical substance that's like this. Okay? Water has a unique phase diagram that we want to be able to tell the difference between. So for water, its plot diagram looks something like this. I kind of exaggerate that line there. Solid, liquid, gas, pressure, temperature. That is the defining characteristic. The angle of the crack lets you know that you have water, okay? Characteristic for H2O graph. Right? That's how you know that you have a water diagram. Okay, you have the the crack line is got a slope going the other direction. Okay, that's how you know. Otherwise, the graph works the same way. All right, the graph works the same way. All right, there's still a triple point. All right, there's still the critical point. All that stuff's the same. All right, so that's pretty much it. Okay. All done for today. Okay. Got some practice problems for you.